Introduction. Look, Deepak, what I got. I have a torch. Yes, it is. But I don't think that you have better than mine. Look what I have. I have a laser light. Laser light? Wow, it is quite fascinating. My father gifted me on my birthday. My father told me that this light is very dangerous for eyes. But how does a light can harm our eyes? Actually, it is a light of narrow frequency, and light has its application in the field of physics. Can you tell me more of it? Yes, sure. In this lesson, you will learn about the dual nature of matter and radiation. Objectives. At the end of this lesson, you will be able to explain the electron emission, explain the photoelectric effect, discuss wave theory of light, state Einstein's photoelectric equation, find energy of photon, explain the particle nature of light, explain wave nature of matter, state Heisenberg principle, explain Davison and Germer experiment. Electron emission. In some solids called metals, the electrons, particularly outer ones, are so loosely bound to their parent atom that they can easily move from one atom to the other and move about in the solid. These electrons are called free electrons as they are free to move inside the solid but cannot leave the solid on their own. These electrons are held inside the metal surface by the attraction of the ions and of surface forces. Thus, these electrons require a certain amount of energy in order to come out of the metal surface. The minimum amount of energy required to emit electrons out of the metal surface is called the work function, phi0 of the metal. This minimum energy work function required for electron emission from the metal surface can be supplied to the metal in any of the following ways. Field emission. Electron can be made to leave the metal surface by applying strong electric field. Thermionic emission. By heating the metal, sufficient thermal energy is received by the free electrons to overcome the attractive pull of metal surface. Photoelectric emission. Free electrons from the metal can also be released by supplying energy to them in form of light. Photoelectric effect. The emission of electrons from metallic surface by light energy is called the photoelectric effect, and the electrons so emitted are called the photoelectrons. Hertz observations. While performing an experiment for production of electromagnetic waves by means of spark discharge, Hertz observed that sparks occurred more rapidly in the air gap of his transmitter when ultraviolet radiations was directed at one of the metal plates. Hertz could not explain these observations, but other scientists did it. They said that the cause was the emission of electron from metal plate due to incidence of high-frequency light. This is photoelectric effect. Hallwalks and Lenard's observations. Philip Lenard observed that when ultraviolet radiation was made incident on the emitter plate of an evacuated glass tube enclosing two metal plates called electrodes, current flows in the circuit. These observations indicate that when ultraviolet radiation fall on the emitter plate, the electrons are ejected from it, which are attracted to its anode plate. The electrons flow through the evacuated glass tube, completes the circuit, and current begins to flow in the circuit. Then Lenard and Hallwalks studied further by taking a zinc plate and an electroscope. The zinc plate was connected to an electroscope. They observed that when an uncharged zinc plate was irradiated by ultraviolet light, the zinc plate acquired positive charge. When a positively charged zinc plate is illuminated by ultraviolet light, the positive charge of the plate was increased. When a negatively charged zinc plate was irradiated by ultraviolet light, the zinc plate lost its charge. All these observations show that when ultraviolet light falls on zinc plate, the negatively charged particles, that is, electrons, are emitted. Assessment. Before proceeding further, let us know how much have you learned. Match the following. experimental study of photoelectric effect, apparatus and circuit. The tube containing two electrodes, P and Q, has a side window of quartz to permit ultraviolet rays for the experiment. A source of radiation is suitably placed in front of the window such that the radiation falls on Q. P and Q are connected to a voltmeter with zero center. To provide the necessary voltage, we have a high-tension battery B connected to across a potential divider arrangement Mn with a key K. Effect of intensity of light on photocurrent. The photoelectrons emitted per second is directly proportional to the intensity of incident radiation. Effect of potential on photoelectric current. Curve A is for low intensity of the incident radiation and curve B is for high intensity of the incident radiation. The photoelectric current increases with the increasing potential. For a certain potential, the current becomes maximum. After that, increase of potential does not increase the current, and that is called the saturation current. Let the potential of P be now made zero. At this stage, a small current is observed due to the few electrons which, just because of sufficiently large velocity of emission, are able to reach P, even though P does not have any positive accelerating voltage. Now let P be made negative by sliding the running contact L towards N. The current begins to fall off rapidly, and at a given fixed value of potential, minus V0, the current becomes zero, and the photoelectric emission will stop altogether. This voltage, V0, is called the stopping potential. Photoelectric current is zero when the stopping potential is sufficient to repel even the most energetic photoelectrons with the maximum kinetic energy, Kmax, so that Kmax is equal to EV0. Effect of frequency of incident radiation on stopping potential. Photoelectric current remains unaffected by change of frequency, but stopping potential increases with increase of frequency of incident light. If we plot a graph for stopping potential V0 against frequency of incident light, it is in the form of a straight line. If frequency is continuously decreased, the stopping potential becomes zero at a certain frequency. This frequency is called the threshold frequency. Thus, threshold frequency is the minimum frequency of incident light at which the stopping potential or maximum kinetic energy of emitted electrons becomes zero. If the frequency of incident light becomes less than the threshold frequency, the photoelectric effect does not occur. Photoelectric effect and wave theory of light. According to wave theory, the kinetic energy of photoelectrons must depend on the intensity of incident light. But according to experimental observations, the kinetic energy of photoelectrons does not depend on the intensity of incident light. According to wave theory, the light of any frequency can emit electrons from metallic surface provided sufficient intensity of light. But according to the experimental observations, the light of frequency less than threshold frequency cannot emit electrons, whatever the intensity of incident light may be. According to wave theory, the energy transferred by light waves will not go to a particular electron, but it will be distributed uniformly, so emission of electrons will take some time. But experimental observations show that the emission of electrons take place instantaneously after the light is incident on the metal, whatever the intensity of light may be. Einstein's photoelectric equation. Energy quantum of radiation. Light propagates in the form of small bundles of energy called quanta or photons. The energy of each photon is h nu. When u is the frequency of light and h is the Planck's constant. The value of h is 6.62 into 10 raised to the power minus 34 joule second. If the electron absorbs the energy from photon more than the energy needed to escape out from the metal surface, that is phi 0, then the electron is emitted with maximum kinetic energy Kmax, which is equal to h nu minus phi 0. This equation is known as Einstein's photoelectric equation. Important points. For the emission of electron from metal surface, h nu greater than phi 0. This shows that greater the work function phi 0, greater the threshold frequency needed to emit the electron. The more the number of photons available, the more the number of electrons absorbs energy from the photons, and therefore greater is the number of electrons emitted from the metal surface. We know that Kmax equals EV0, and Kmax is equal to h nu minus phi 0. So, h nu minus phi 0 is equal to EV0. EVO is equal to h by E into nu minus phi 0 by E. If we plot a graph between nu and V0, taking nu on x-axis and Kmax on y-axis, the graph is a straight line, since equations is of the form y, which equals mx plus c. The slope of the line m is equal to h upon E, which is a universal constant. Example: if light of wavelength 4000 to 950 angstrom is viewed as a continuous flow of photons, what is the energy of each photon in EV? Given Planck's constant h as 6.6 into 10 raised to the power minus 34 joule second. Solution: the energy of photon can be found by E as h nu, E equals hc by lambda, name it as equation 1. C is the speed of light, which is 3 into 10 raised to the power 8 meter per second. From equation 1, E equals 6.6 into 10 raised to the power minus 34 into 3 into 10 raised to the power 8 by 4950 into 10 raised to the power minus 10 joule. After solving, we get E as 4 into 10 raised to the power minus 19 joule. It can be expressed in EV, E as 4 into 10 raised to the power minus 19 by 1.6 into 10 raised to the power minus 19 EV. E is equal to 2.5 EV. Particle nature of light, the photon. The photoelectric effect supports the Einstein's quantum theory of light, which states that the light in interaction with matter behaves like bundles of energy, each bundle being called a photon. The photon picture of light can be summarized as: when radiation interacts with matter, it behaves as if it is made up of particles called the photons. The energy of each photon of frequency nu and wavelength lambda is E as h nu, which is equal to hc by lambda. The momentum of a photon p is equal to h nu by c, which equals h by lambda, where c is the speed of light. All photons of a given frequency have the same energy E, which is equal to h nu. The photons are electrically neutral, so they are not deflected by electric and magnetic fields. In photon-electron interaction, the total energy and total momentum are conserved. However, the number of photons may not be conserved in a collision because photons may be absorbed and new photons of different energies may be created, so that total energy may remain constant, that is h nu, which equals h nu 1 plus h nu 2. Wave nature of matter. In 1924, Louis de Broglie proposed that material particles in motion behave as waves, and the wavelength associated with the material particles is given by lambda is equal to h by p, which equals h by mv, where p is equal to mv is the linear momentum of the moving particle. This is called de Broglie hypothesis. The momentum of the photon is p is equal to h by lambda. This gives wavelength lambda as h by p. Therefore, de Broglie proposed de Broglie wavelength lambda is equal to h by p, which equals h by mv. If k is kinetic energy of material particles, then the relation between momentum p and kinetic energy k is k as 1 by 2 mv square, which is equal to 1 by 2 into m into p by m square, which equals p square by 2m, or p as square root of 2mk. Hence, de Broglie wavelength lambda is equal to h by square root of 2mk, name it as 1. If V volt is the accelerating potential of electron, then k is equal to EV from equation 1. Lambda is equal to h by square root 2 mev. Substituting the values of m, e and h we get lambda as 12.27 by square root of V angstrom. Example. Calculate de Broglie wavelength associated with electrons accelerated through a potential of 5 kilovolt. Solution. Given V is equal to 5 kilovolt, which equals 5000 volt. From the formula given below, we can find the de Broglie wavelength. Lambda is equal to 12.27 by square root of V angstrom. Lambda plus is equal to 12.27 by square root 5000 angstrom, which equals 0.173 angstrom. Wave packet. According to Heisenberg, it is impossible to measure both the position and momentum of a material particle exactly at the same time. The product of uncertainties in simultaneous determination of position delta x and momentum delta p is of the order of h cap, where h cap is equal to h by 2 pi. Delta x into delta p approximately h cap. A wave of definite wavelength extends over all space, but an electron, which is represented by wave, cannot occupy all space. Therefore, it was suggested by Max Born that a material particle, say an electron, is not equivalent to a single wave, but it is equivalent to a wave packet, which is superposition of a number of waves of varying frequencies and results in a finite region where waves interfere constructively and the particle has maximum probability of occurrence in this region. This region is called wave packet. Davison and Germer experiment. The given figure shows the setup of Davison and Germer experiment. The electrons are accelerated to the desired energy by applying potential from a high-tension HT battery to a cylinder A, having fine holes along its axis so that a fine beam emerges along the axis of the cylinder. The beam is directed at a block of nickel crystal known as the target T that is capable of rotating about an axis parallel to the incident beam direction. The electrons are scattered in all possible directions by the atoms of the crystal. The intensity of the scattered electron beam in a particular direction is measured with a Faraday cylinder called the collector C. The collector can be moved along a graduated cylinder scale S and is connected to a sensitive galvanometer. The deflection of the galvanometer is proportional to the intensity of scattered electron beam entering the collector. The variation of the intensity I of the scattered beam with the scattering angle theta is measured for various electron energies. From de Broglie relation, the de Broglie wavelength associated with the 54 eV electrons can also be determined. For these electrons accelerated through a potential difference of 54 V, lambda is equal to h by p, which equals 1.227 by square root of V. Nanometer is equal to 1.227 by square root of 54 nanometer equals 0.166 nanometer. The Davison-Germer experiment thus provides direct verification of de Broglie hypothesis of wave nature of material particles. Did you know? In 1905, Albert Einstein was a German-born theoretical physicist who explained the photoelectric effect. In 1924, Louis de Broglie gives his theory on wave-particle duality. Summary. Let us summarize what we have learned. The minimum amount of energy required to emit electrons out of the metal surface is called the work function phi0 of the metal. The energy can be supplied in three ways: field emission, thermionic emission, photoelectric emission. The emission of electrons from metallic surface by light energy is called the photoelectric effect, and the electrons so emitted are called the photoelectrons. Photoelectric current depends upon intensity of incident light, applied potential, frequency of incident light. Einstein's photoelectric equation. Kmax is equal to h nu minus phi0, where Kmax is the maximum kinetic energy. Nu is the frequency of light. Phi0 is the work function of the metal surface. Einstein's quantum theory of light states that the light in interaction with matter behaves like bundles of energy, each bundle being called a photon. The energy of each photon of frequency nu and wavelength lambda is E equals h nu. de Broglie wavelength lambda is equal to h by square root of 2 mk, where k is kinetic energy of material particles. Heisenberg principle states that it is impossible to measure both the position and momentum of a material particle exactly at the same time. The Davison-German experiment provides direct verification of de Broglie hypothesis of the wave nature of material particles.